Hi and welcome to the third in our series of PFAS remediation webinars. Thank you for joining us. My name's Connor Walsh. I'm the CEO of OPEC Systems. I'm joined today on the sofa with Peter Murphy, our Managing Director.
G'day guys.
Dave Burns, our lead scientist. And today we have the privilege of Dr. Dora Chaing from CDM Smith joining us from the States. We want this to be a really interactive webinar. So in the bottom right-hand corner of your screen, there's a chat box. We encourage you to type your questions in there. And at the end of the webinar, we'll come back and answer those questions to the best of our ability. We're aiming for a 60-minute webinar with the Q&A session at the end of that 60 minutes. It's a fantastic turnout. We've had over 350 people register for this webinar. If you missed our first two webinars, the first webinar was on the principles of foam fractionation, and the second webinar was a walkthrough of the water treatment plant that we've put in the Okey Army base in Queensland. Go and have a look at our website. You'll see both of those webinars there. It's on the screen for you now. The agenda for today, well, certainly a lot has happened since our last webinar. COVID-19 has impacted the world and how we do business. You'll see us socially distancing here. We're 1.5 metres away from each other. But it has been an exciting time for us as a company during that challenging few months. We've hit the 1 year milestone for the Okey water treatment plant, and we're going to take a look at some of the data we've been analysing over this past 12 months that have come out of that plant. We're also going to look at how we've refined that big SAFF treatment plant and how we've tweaked that, lessons learned, and put it into a really neat containerised 40-foot solution there. So we'll do a fly through on that. We're then going to go through the three critical phases in any successful PFAS remediation program. And that's the separation, the concentration, and the destruction. And that's where we'll have the privilege of Dr. Chaing joining us to talk about CDM Smith's development in electrochemical oxidation destruction cells. And then we're going to break down for the Q&A session of the webinar. So without any further ado, Pete, perhaps you can share with us the big news coming out of OPEC's Okey SAFF system.
Yeah, sure, mate. Hey, everyone. Good to see you all again. So we are now beyond the 1 year anniversary of the SAFF plant up at Okey. So we commissioned that plant in May of last year, and we've just celebrated the 1 year anniversary. We started installing that plant in December of 2018. So we've been sampling, both internally sampling and also had the client's environmental consultant sampling the performance of that plant over that period. So now we've got a really robust data set to be able to assess how the system's going, where it performs, where it doesn't perform, and how well it's going. So really looking forward to taking everybody through that process. And I guess that there's a lot of lessons learnt after a year of operation. So we've been able to tweak it. But I'm happy to say in that year's time, we've treated over 30, or just under, I should say, 30 million litres of water, so quite a good volume. From that, we've produced about 1,200 litres of secondary fractionate, which is our PFAS concentrate. And from that 1,200 litres of PFAS concentrate, over the last month, we've been working on the tertiary fractionation process, which dewaters that fractionate. And the results we've had 400 litres treated, diluted that down to a couple of litres. So we're expecting that from the 30 million litres we've treated, we're going to end up with somewhere between 6 and 12 litres of highly concentrated PFAS waste material. So it's just the concentration steps that we're getting there have been amazing. So looking forward to sharing some data on that as well.
Yeah, it is very, very exciting. So Pete, for those people who missed probably webinar 2, which did a complete walkthrough of the Okey water treatment plant, I'm just wondering if you can just give us a quick overview of Okey and the facility we've got up there.
Sure. So Oakey's a site in Queensland in Australia. It's a little bit west of Brisbane. And there's an Army Aviation Centre up there that has had firefighting training areas in a few different locations. And like a lot of sites around the world, this firefighting foam has caused contamination in the aquifer and the subsurface conditions up there. And so you can see on the image on your screen, there's quite an extensive plume extending down gradient for some kilometres from the site at various concentration levels. And so in 2018, Defence released a tender for 4 defence sites. We were lucky enough to win the OPEC project, where we've installed a 250,000 litre a day plant up there.
Okay, well, I think we've got now just a really condensed version of the webinar too. We've got a 3-minute video, which we'll just throw to now, which will show that water treatment plant up at Okey.
Just a quick recap.
G'day, I'm Peter Murphy, OPEC's Managing Director, and welcome to a wet day at the Army Aviation Centre up at Oakey in Queensland, which is in Australia. We're here today specifically to look at the surface active foam fractionation element of the plant. This first stage in these large vessels, we call that primary fractionation. It's fairly straightforward. You guys will have seen, no doubt in your experience, DAF plants. You'll have seen sparging plants in sewage treatment. You'll have seen lots of ways where water and air are mixed and you'll get a foam at the top. What we're doing is we're just taking a cut of that foam using a simple spillover weir approach, and it just helps us to elevate our PFAS levels from a baseline of about 1 part per billion in the groundwater, gets us up 5 to 10 parts per billion, so we just get a healthier foam. The treated water, all of the long chain compounds essentially are removed at this stage, and a large proportion of the shorter chains. Every litre of water only goes through one of these. They don't pass from one to the next. It's just each one of them treats its water. The wet cut comes off. It accumulates in a vessel around the back here. And that wet foamate is then delivered to the secondary fractionator. So this patented vacuum harvesting system for foam is what really makes the difference. Just using traditional spillover weir designs, you're getting a 10-fold step. You go here and you're getting a 1,000-time concentration step. So between these two stages, we're getting 10,000 times concentration. So you can see this beautiful foam starting to emerge here, and we don't get the opportunity to do this tertiary fractionation stage very often. Over the last 9 months, we've only produced 2,000 litres of secondary fractionate. So we've only had a couple of opportunities, and we've had results quite good between 5 and 60 times concentration factors, which overall are giving us about a 400,000 times concentration factor. But we're really confident with a little bit of work, we can get this concentration factor in the tertiary stage to between 100 and 1,000 times, which will bring us up to between 1 million and 10 million times overall concentration factor. So the issues of separation and concentration are undertaken in a single step using 3 different stages of fractionation that allows us to take large volumes of water that are contaminated by potentially low or average levels of PFAS and condense that PFAS contamination down into incredibly small volumes. So not only does the issue of what consumable use go away, we've also solved the issue of waste to a very large extent. We would argue that this is a primary lifter in any PFAS treatment train. We've taken 5 years to develop the system. We've now proved it for a year with third-party validation and some just amazing results. And we have proven beyond a shadow of a doubt that physical separation and the SAFF system is the heavy lifter in the PFAS remediation equation.
Yeah, that's a great summary, and I hope people enjoyed just getting that very quick 3-minute summary. Dave, that brings us, we've now got 12 months worth of data under our belts from that facility. Can you talk us through that data and what it means?
Yeah, sure, Connor. So we've got some great graphs that we'd like to share with you.
Love a good graph.
It shows the performance of the Okey plant. So up at Okey, we monitor about 32 PFAS compounds on a weekly basis. And in this ribbon graph, where we're monitoring these 32 compounds, and there's about 14 PFAS detectable PFAS compounds in the feed water. The graph's showing the feed water concentrations, the post-SAFF concentrations, and the final polishing anion exchange resin concentrations. And you can see in this first graph that the 3 target contract compounds that we work for up at Okey, PFOS, PFHXS, and PFOA, we remove those down to 2 parts per trillion, 3 parts per trillion, and 20 parts per trillion. So under the adopted criteria of 70, quite easily. Basically, it's an 81.7% bulk detectable PFAS reduction. So if we go to the next slide, this slide shows the PFOS, PFOA, PFHXS ribbons pulled out of that stacked feed water graph. Just more elegantly shows how we meet the criteria without any polishing.
Just air bubbles are getting us down to that level.
Just simple aeration of water. And then if we have concerns that more stringent criteria may come into the Australian market in the future, we can take a look at some criteria in Sweden where the sum of P11 with a total 90 parts per trillion criteria could be applied. But you still see from this graph, Pete and Connor, that SAFF does the bulk heavy lifting. It removes the bulk of the PFAS quite rapidly, 25-30 minutes of aeration, so that a polishing technique doesn't have to work as hard, it's conserved, and it's more easily able to fit into our total life cycle treatment philosophies.
Yeah, I mean, it's this concept of the heavy lifter that we've talked about a few times, but when we're getting, well, it's always a bit dangerous dealing in percentages, but 100% of long chains down to 1 part per trillion. And then the shorter chains, as we'll show in some of the predictability modelling that we do a bit later, we're removing varying percentages of that as well. So overall, that SAFF is doing about 81.5% of the bulk detectable.
There is one more slide that shows our predictability removal rates. So as I mentioned before, we're collecting lots of data that's feeding into our data handling system. So for 12 months on from Okey, we're pretty certain that we are locking in a 100% removal rates down to that 1 ppt LOR for the long chains. Some of the shorter chains where we still would need to rely on a little bit of polishing with resin, typically like your C3s up to some of the C5s, we've got up in this table here. There's a little bit more work for us to do, which we're currently got going on at the moment.
Fine tuning. Well, that because coming out of that Okey site, one of the things we have been working on is these bench scale units. So Pete, can you just talk us through those bench scale units and what they mean?
Yeah, I guess we were inspired towards the end of last year to start spreading the gospel of SAFF, if you like, and so we had gotten some good results, but we understand that it's a global market, and a lot of the offshore territories that we were targeting really wanted to get some results based on their own water chemistry and their own lithology, and all that was fair enough. So we put the engineering and design team to work, and over about 3 months we built our bench scale SAFF units, which are about a 1 to 50 scale SAFF plant. And so what we're able to do with those plants is run a sort of a treatability study, if you like, on a client's water source. So first of all, we can give them, using our predictability model, we can do a bench scale or bench top exercise to say, look, we think you're probably going to achieve this level of result based on your particular PFAS signature. So bearing in mind excellent performance for long chains, declining performance for the short chains. Based on your mix, we'll be able to tell you just how much work you're going to do. And then
what do we got on the screen here?
Oh well, this is a great slide actually. So this is so Uppsala Vatten, which is just north of Stockholm, are a water utility that have currently got one of the bench scale units, and they're treating it on one of the leachates from one of their landfill sites. So you can see a really heavily contaminated mix of various things that you get out of landfills coming in, and yet the fractionation process is still working really elegantly there. You can see the foam just spilling over the hood at the top. We're able to get that wet cut efficiently, and this is, for me, this is sort of part of the beauty of fractionation, is it's a really robust agricultural style of technology. It uses pumps, valves and venturis to be able to generate air bubbles and separate out using physical separation techniques. So that was, we were able to look at it in leachates, and then I guess at the other end of the spectrum, we've also been looking at some of the clearer waters, the site surface runoff waters, drinking waters, these various other environments where you're getting PFAS contaminated water as well. And so, of course, it's this is quite a contrast, I suppose, between those two sites, but the beauty
the same objective is to get the PFAS
it's about removing PFAS molecules, and it does it well in that, even across a variety of applications.
So we've got two of those bench scale units. One's, I believe, in Sweden.
One's in Sweden, and then one's with at the CDM Smith laboratory in Bellevue, which is just out of Seattle in the US. So both of those plants are in the midst of quite getting quite booked up with treatability trials, just to validate the technology in those territories.
So it's good, because Dave, this is what you've always been sort of looking for, is where we can do that desktop review of people's water and what it's contaminated with.
So if people out there have laboratory test results of their feed water, you can email them to us. We can do a quick desktop review and give an indication of the % removal rates per PFAS compound. And then if you want a little bit more confidence, you can ship in 40 to 80 litres of water to our lab in Sweden, CDM Smith in Seattle, or our research partner here in Sydney, which is Macquarie Uni. We can run the benchtop.
Right, and so we can do it in Australia as well, because I know we had a lab down in Melbourne, but it's moved up to Macquarie Uni. So that then allows people to just get a bit of certainty before they go and invest in a major water treatment.
Yeah, it's a big investment, a water treatment plant.
Yeah,
we want a client to be confident that it's going to work.
Absolutely. So, just to our audience there, again, if you've got questions, just put them into the chat box down in the bottom right-hand corner of your screen, and we'll come back to those at the end of this webinar. So, coming out of that, Pete, we've then gone and designed SAFF 2.0, which is the next the evolution of our SAFF system. So, talk us a little bit through that SAFF 2.0.
Yeah, well, I guess there's no benefit like experience from design and engineering point of view, and so through our partners Envitech over in Sweden, we were able to we got an order for a full 40-foot containerised system earlier in the year, and so that was a great opportunity for us to take all those lessons learnt from the Okey site and then embody them into a single containerised 40-foot version. We've got another unit heading across to the States later in the year, so we're producing those units internally. OPEC's fortunate enough to have an internal design and engineering capability that allows us to take full control of the production of these systems, and we're really looking forward to shipping those systems away in late September, October this year.
We've got a walkthrough of that SAFF 2.0. So can you talk us through the sort of key features of the
Sure, yeah. So the system is designed first and foremost to be fully containerised. So we wanted to create a plug-and-play environment where we could undertake the primary, secondary and tertiary fractionation steps within a single portable modular containerised footprint. So you can see we've got fairly good access doors all the way around the system. The system's fully insulated with environmental control systems, quite a flash one inside that just maintains the operating temperature. As we move through the system, we've got some initial primary filtration just to take out solids. And then one of the things I really like about this is the control system is contained in one end of the SAFF 2.0. So we've got a 600 mil kind of 2-foot area there where all of the human machine interface, the PLC systems, all of the telemetry controls are all housed in that particular area. And so an operator can come up, they can work on the plant, they can make all the adjustments. We've really spent a lot of time in the engineering side making it adjustable remotely. So, for example, a plant could be anywhere in the world, and we can adjust all the key parameters around flow volume, processing time, vacuum pressures, and so on from anywhere, as can the client. They can at any point in time look at its performance in real time and see how it's going. So that's been a big step, and that room keeps the operator away from the PFAS concentrates in the operating environment, to just another level of safety. So effectively, these systems arrive on site, they're bunded, fully self-bunded. So as long as you've got a hard stand and a place to pop it, all you need effectively is you plug in a power line, a 3-phase power source, and an influent line with your contaminated water goes in. And you'll see that there's actually a return line as well. So we get the water we need. We can just return any overflow that comes into the system. If we move up and we sort of peel away the skin a little bit, you'll see that it's some fairly clever engineering in the way we've compacted it all into a relatively tight space. On the right-hand side, you can see the influent tank. So that's a 3,000 litre tank. Each of the primary fractionators runs in about a 2,600 litre batch. So as that right-hand tank fills up, it gets to a certain level, and then it starts one of the 4 fractionators in the fill process. It's about a 3-minute fill time. We're processing for around about 20 minutes, as we showed in the last webinar. The processing times vary depending on the criteria compounds you're chasing. So for us, chasing PFOS, PFOA and PFHXS, we have a run time of somewhere around quarter of an hour to 20 minutes to remove those contaminants completely. The fractionate or the harvested wet cut runs out the top of the units, and then the treated water, which remains in the vessel, is then discharged and cleaned. So that primary fractionate collects in the tank on the left-hand side that you can see there, the dark grey one. And when it fills up to a level about 1,050 litres, we fill up one of our secondary fractionators. You can see the ones with the tall vacuum head there. Those units fill up, they run through their own automated processing cycle to dewater the primary fractionate and to further concentrate it. So on the right-hand side there, as we said in the video, you're getting about a 10 times concentration step, or a 10% wet cut. But in this secondary stage, that's when you get the real magic happens. And that's where the sort of patent lies and the innovation, I guess, lies, is that we're able to get 1,000 times concentration step in that secondary fractionation step. That secondary fractionate then goes to the light grey tank in the centre, where it's held until a certain volume builds up. And then using the left-hand side fractionator, we're able to conduct a tertiary fractionation step. We've been doing a lot of work in the last 4 weeks or so on tertiary fractionation, and we're able to get between 200 and 500 times concentration step there. So all up, we're now north of 1 million times concentration factor, just using air bubbles. No chemicals whatsoever in the process. There's no absorbent medium or IX resins or anything. We're just using air bubbles to create these phenomenal levels of separation. And then from the tertiary fractionate, that runs into the third tank on the far side, and that builds up there. Bearing in mind that for every, say, 1 million litres, and this unit will process just under 1 million litres a day at the most rapid cycle, it'll produce about 600 mils of tertiary fractionate. So about a milk carton of really concentrated fractionate, which is actually getting back to the concentration levels that it was introduced into the environment as a firefighting foam in the first place. So we're really turning back time.
Really closing the loop, aren't we?
Yeah, it's incredible.
Well, we'll get to closing the loop shortly, because I think that then we're then storing it here either for destruction or removal.
That's right. So once you've got the tertiary fractionate, Dora will go into way more detail with us, but basically it's then available as a tiny concentrated volume to get rid of using a variety of techniques. We're trying to work on a sort of a holy grail, if you like, which is to conduct the destruction of the PFAS within the unit itself or adjacent to the unit, using the kind of technologies that Dora is going to talk about. So yeah, it's very exciting stuff, and I just like I'm really proud of our engineering team in that they've been able to just not only just compress it into a container and actually double its capability, but they've also been able to make it really robust for field transport. So a lot of design work's gone into hardening the system.
Yeah, not only they compressed the thing, it was in a compressed time frame from memory as well.
Yeah,
so
we only had a couple of months to get that done, but they've done an awesome job.
it is a very elegant solution. Well, look, it's funny because I have got some questions coming through, so I would encourage you again, just in that chat box at the bottom of your right-hand corner of the screen, please put your questions in there. But I kid you not, this is not a seated question, but I have a question from Mauricio. I'm sorry, Mauricio, if I've got that wrong, but is OPEC working on a mobile SAFF treatment plant? Well, hopefully that answers your question there.
I guess, Mauricio, the other option is to trailerise that system as well, and we are looking at that with some partners in the US. So I think either in a container or on a trailer-based platform is the way to achieve that.
And then Mauricio then goes on to say, is there a minimum flow rate required to run the SAFF plant? And I guess...
Well, not really, Mauricio. I mean, so we've got the initial holding tank for the influent water needs to reach a certain level before it fills up the first primary fractionator and starts the process. So there's no minimum flow rate. It's just that, there is a maximum flow rate, which for that system is about 960,000 litres a day.
I guess if you remember that it's a continuous batch mode, so if there's not enough flow, the system will just be on standby until the fill tank reaches full, and then it'll process it.
Kick off
or if it's always filling, it's always continuous batching.
James, I see your question. We'll come back to that at the Q&A. I just thought that was just such the timing of that question came through perfectly. So now we're going to get to what we see as the three critical phases of any successful PFAS remediation program, which is the separation, the concentration, and then the destruction. And the destruction's where we'll have our guest speaker, Dr. Dora Chaing, join us. So Dave, just talk us through the separation phase, please.
Okay, so foam fractionation works on this principle of where a PFAS molecule has a hydrophilic water liking or soluble functional head chemistry and a hydrophobic water less loving tail. And basically when we introduce air bubbles into a water column, the PFAS molecule orientates the head to be in the water and the tail to be out of the water. And when the PFAS molecule attaches itself to a rising air bubble, the air-water interface, the rising air bubble carries all the PFAS molecules out of the water column up to the surface of that water column, the meniscus, forms a foam, and we whisk it away. So it's quite a simple process, but there's a very tricky art to get that right, to make sure that the primary fractionation process removes the PFAS to below your adopted criteria. And that's the science.
Yeah, I think most people on the call, you would have seen industrial processes that generate foams. I mean, it happens naturally on lakes and on beaches, and it also happens in sewage treatment plants and leachate plants and so on. And so that mechanical agitation, in effect, that the energy that the air bubbles creates, it releases the foam. It gives it because of the physiochemistry of the PFAS molecules, they're very amenable to fractionation, and then they float up. And then we just sort of take that very top layer, including a fair bit of water, and we just float it over the top. And in that allows us to really effectively and simply achieve a separation step.
So that's the separation. So let's look at where I think the real magic happens is the concentration. So, well, I think the magic happens in both phases. But
more magic.
More magic. That's the magic. So let's have a look at that concentration phase. Pete, do you want to talk us through a little bit about the concentration?
Yeah, so concentration is really where the art happens. And so that's the hard bit, if you like. And so what we're trying to do is take the primary fractionate that we get off that first step, and then we've got to dewater it. And we want to dewater it a lot because we're dealing with, millions of litres. And so even if you're only getting 1 or 2%. It's way too much to practically deal with. So we have to get really good concentration factors for this to be effective for our clients. So secondary fractionation is similar in that it uses the physiochemistry of the fluorocarbon compound to rise and accumulate as a foam at the meniscus. But then we are the space between that layer of foam and our vacuum hood. We're sort of adjusting parameters around vacuum pressure and foam height and also the water level within the tank to be able to just create the optimal conditions for us to draw off a really sweet, dry foam. And if we get that right, and as Dave said, I guess that's where the art and the IP lies. If you get that right, then you can get about 1,000 times concentration step right there. And then if you do that again and get another 200, 500,000 times in the tertiary fractionation, all of a sudden, for every Olympic pool's worth of water that you've treated, you've generated about a coffee cup's worth of fractionating. So we're getting that now. We're up over 1 million times on the Okey plant, and so that literally is a coffee cup from an Olympic pool.
Wow. That definitely is the very heavy lifting of a water treatment plant. Which brings us neatly into what do you do with that coffee cup of PFAS. So I have the privilege of introducing our guest speaker, Dr. Dora Chaing, who has a PhD and is an engineer and is without a doubt an internationally renowned environmental remediation PFAS expert from CDM Smith in the States. Dr. Chaing, thanks for joining us. What can you tell us about electrochemical oxidation, the AACO destruction cell that PDF Smith have been working on in this CDM Smith, sorry, been working on in the States, and what's the synergy between that and the OPEC SAFF system?
Thank you, Connor. I hope you can hear me okay. Before I talk about electrochemical oxidation or ECO, I do want to spend a few minutes to just generally introduce PFAS destruction. Next slide. So what is PFAS destruction? PFAS destruction typically means to break the carbon-fluorine bonds through engineering processes and ultimately to mineralize PFAS really without leaving any unwanted fluorinated organic behind. So we do know that carbon-fluorine bond is one of the strongest bonds in the chemistry, so it's difficult to break. So completely breaking carbon-fluorine bond is not that easy, even though everyone talking about PFAS destruction. So actually, during the destruction processes for PFAS, it's very easily to find the fluorinated intermediates. They can be generated before PFAS are completely mineralized. So how do you really know that PFAS are truly destroyed and not transformed or precipitate out during the destruction process? So right here on this slide, I included 3 lines of evidence that we can utilize to validate whether PFAS destroyed. That include disappearance of target perfluoroalkyl acids, generation of fluoride, and reduction of total organic fluorine concentrations. So it's very almost required in order to convince the audience that we do have destroyed the PFAS. You need to have those 3 lines of evidence. On the other hand, that we also frequently hear about the precursor transformation. Precursor transformation really lead to some terminal or what we call the dead end products, perfluoroalkyl acids. Like you see on the slide here, that fluorotalumide alcohols are transformed into perfluoroalkyl carboxylates. And when the transformation is terminated, it actually accumulates more perfluoroalkyl acids. So that can potentially increase the risk to human health. So that is really not what we want to see. Next slide. So how can PFAS destruction be applied in a real-world situation? The commonly known option for PFAS destruction is off-site incineration, which is not considered as an emerging technology. And we are not sure yet if incineration can completely destroy PFAS. We talk about it requires very high temperatures, but also there are some evidence that even high temperature cannot completely destroy PFAS. So for the emerging destruction technology that we all talk about and focusing on development, the current focus is really trying to apply the PFAS destruction in situ or ex situ at a site, but typically it will be ex situ simply because it's a lot more easier to control the conditions, including the energy and temperature for breaking down the carbon fluorine bonds. So destruction technology can be considered for mainly the highly impacted water or wastewaters. Really, the use of destruction technology directly destroy low concentration of PFAS is really cost prohibitive and it's not going to be efficient. So it makes a lot more economic sense to separate and concentrate PFAS that they and P repeatedly talking about like concept about separate, concentrate, and destroy. So low concentration situation is much more making sense to go through the separate, concentrate, and destruction process. Right now, there are some removal technology, PFAS removal technology. They can generate high concentration and low volume of PFAS waste stream. Those technology including regenerable ion exchange resin, foam fractionation, soil washing, reverse osmosis, chemical electrochemical coagulation processes. And this technology are actually great candidates to couple with destruction technologies. So next slide. So on this slide, I included two PFAS destruction technology that have moved from bench-scale study to field demonstrations, which are electrochemical oxidation and plasma technology. The images to the right are from a ENCT article published in 2019. It's a field demonstration project funded by US Air Force to use plasma technology to destroy PFAS in IDW. So it demonstrates very high efficient destruction of long-chain PFAS, which you can see on the left-hand side of that bar chart right there. And it does generate our short-chain PFAS as intermediates. And we also have seen some precursors concentration have increased from the transformation of other precursors in the water. So far, we still have a lot of challenge, particularly for destroying short-chain PFAS and precursors, but we do believe it's a matter of optimization and maybe the destruction technology do take a longer reaction times in order to achieve the better results. So another point I want to make on this slides, although field demonstration are ongoing for those two technologies, their cost impact on life cycle cost is still unclear. But we do expect, like we see the previous slide, that you are going to generate such a small volume of the concentrate. So we believe that even though it's a high energy technology, but ends up is going to treat such a small volume of waste stream, the cost impact is not going to be significant. So next slide, please. Thank you. So at CDM Smith, the research on electrochemical oxidation really started back in 2015. Over the past 5 years, we have tested to destroy PFAS in different types of waters and wastewater in the laboratory scale. So our research team really focused on the use of boron diamond BDD electrode that is already commercially available for industrial wastewater treatment. And you can see on the right-hand side, based on the 8 hours treatment time, we got a total of 80% PFAS reduction, and there's no increase in short-chain PFAS, luckily, in this case. So we do know if the water has a high salinity, it can enhance the electrochemical destruction of PFAS. However, it also can generate perchlorate in this case through secondary oxidation. We found perchlorate generation is very difficult to avoid, particularly when we deal with the real situation, the water samples. But fortunately, perchlorate is relatively easy to be degraded biologically. So we do suggest we do need a contingency plan in order to include a post-treatment unit in order to degrade perchlorate. Next slide. So sorry for this busy slide, but the main point for this slide to show you in terms of the number of different destruction projects that we are currently working on. All these projects that you see shown on the slide are mainly focused on electrochemical technologies. There are some other destruction technology we are currently funded and evaluated, but this slide mainly focus on what have been funded. And then we've been fortunate being selected to perform a lot of electrochemical destruction technologies. The funding agency are mainly Department of Defense in the US, as well as some water agencies. So it's really quite impressive resume here. We do appreciate those funding agencies to encourage the research and development on new technologies. Next slide. So in addition to those destruction projects, we also have a good list of publications so far. It shows a good tracking records on peer-reviewed journal articles to prove that PFAS destruction is possible. We're trying to understand destruction mechanism and also to demonstrate the efficiency of the PFAS destruction technologies. So this is a short list of publications that we currently have just on electrochemical treatment. Next slide, please. All right, now go back to foam fractionation. All right, so foam fractionation, as we heard from Pete and Dave, they requires really no chemical additions, no sorbent, so you don't need to worry about disposal, incineration of spent sorbent. The foam concentrate after sequential foam fractionation steps become an excellent candidate actually to couple with destruction technology, including electrochemical treatment. You can see on the slide that OPEC and CDM Smith are collaborating to have a closed loop treatment system to separate, concentrate, and destroy PFAS. You can see the volume actually feed into the ecosystem is really, really tiny comparing to the feed water in 1 million liter right there. So we are dealing with extremely high concentration, very low volume of waste stream for the destruction units. And we also include a closed loop system to feed that effluent from the eco back to the primary foam fractionator to treat them again. All right, next slide. All right, so this slide shows the results of using electrochemical oxidation eco to destroy PFAS in the PFAS concentrate after the tertiary foam fractionator. The left chart shows the recovery of fluoride as a direct indication of PFAS destruction. The chart to the right shows the concentration decrease with time. So within 24 hours, it shows 3 logs of reduction for PFAS and PFOA, nearly 2 logs of reduction on PFBS. PFBA does shows an increasing trend and then declining as it goes. That kind of is not surprise. If you work on destruction technology, pretty much you see the similar trend. The final concentration of PFBA is still higher than infant toward the end of the experiment. However, we are running additional testing to make sure the short chain will also degrade with time. Next slide. All right, what is our next step? As Dave and Pete mentioned, now our Bellevue lab does have the SAFF bench scale unit. That bench scale unit is not a small unit, actually. So it's much larger than you typically deal with the bench scale units. It's now available. We definitely are trying to independently evaluate the feasibility of this foam fractionation technology. At the same time, we continue to work with OPEC and the other researchers on optimizing our closed loop approach, separation, concentration, and destruction approach. In order to scale up ECO, the electrochemical oxidation process, we have decided to use a commercially available module. That available module using BDD as the anode will help us to scale up very easily in the future. We can put several modules together for the full-scale applications. Things like that is not really proprietary. It's really focused on promoting the PFAS destruction technology. So this scaled up system will definitely provide much higher surface area in order to increase mass transfer and increase the right electrochemical degradation of PFAS. So next slide. All right, so this is my last slide. I really appreciate OPEC for this opportunity to present a PFAS extraction here. So if you have any questions on electrochemical oxidation, please feel free to contact me. I also include a link where you can actually find our PFAS newsletter. Feel free to sign up on our PFAS newsletter, and the link will bring you to the PFAS extraction technology newsletter. So thank you. Back to you, Connor.
Dora, thank you so much for that. Informative and certainly just shows the SAFF and ecosystem as to just how tightly integrated they could be. It seems like a very elegant solution there. Pete, we're just going to quickly look at some of the different remediation technologies that are in the market at the moment, and just do a bit of a benchmark comparison if we can. Do you want to just talk us through?
Yeah, sure, mate. So, I mean, obviously every site and every client has their own kind of differing needs. And so we were trying to just look as objectively, although of course I am slightly biased, but the objectively, what are the parameters that you might want to look at in evaluating any system for PFAS water treatment. So for me, they kind of fall into two camps. There's a sort of subjective and objective, sort of qualitative and quantitative aspects to it. So if we look at the sort of the subjective aspects, you want to understand, well, technology maturity. Has it been used in other industries, other applications? How long has it been around for? And so we've sort of looked at the primary technologies that are available for PFAS treatment. So GAC is a tried and tested favourite. You've got ion exchange resins, both the non-regen and more recently some really great steps forward in regenerable technologies. You've got RO, been around for a lot of decades and it does an excellent job at removing PFAS. You just got to work out what to do with the brine. And SAFF, which is, at 5 years old, is a bit of a new kid on the block. In terms of affordability, if I just move to the third column, you want to understand, how much are these plants going to cost to put in up front. And so that CapEx equation is definitely considered by the client. And I think SAFF is sort of up there with non-regen resin systems and GAC. It's certainly comparable from what we would understand in terms of what can the system deal with. I mean, I think the limitations of a system are important to know, and so we make no secret with the SAFF system that foam fractionation is brilliant for long chain removal and progressively less effective as you move towards shorter chains. So if shorter chains are part of your criteria compound group that your regulatory environment is dealing with, then you'll probably need to use SAFF in combination with a polishing capability. So that short chain removal element's important, whereas RO, excellent for that short chain removal. If I just move to the right-hand side, sorry to chop around a bit, but this element of sustainability for us is really important. Just using air bubbles to remove PFAS for us is probably we imagine is one of the most sustainable techniques that you could come up with. Like, it's hard to imagine a less harmful or intrusive technique. It uses no consumables, it generates almost no waste, and it just harnesses air bubbles to do the work, which is of course free. So it's great from that perspective. Other systems that use more consumables, whether those consumables be membranes or absorbent media, obviously we would view them as not as sustainable. And so they're the sort of the subjective elements, but then you've got 4 cost centres that make up your OPEX, your operating expenditure when you're running a plant. And so they would be the labour that you use, the energy that you use, the consumables that you use, and the waste that you generate. So if we look at those 4 elements, like starting with the consumables, I think the SAFF rates really well because it doesn't use any consumables, so it's hard to get any better than that, really. You've got pumps that will, every now and again require impeller replacements, but by and large there are no consumable aspects to that SAFF plant. Whereas some of the solvent mediums obviously do create consumables, and those consumables convert at some point to waste. And so again, that waste, whether it be in the form of membranes that you get with RO or resins, are going to come at a cost. And over time, those costs actually build up significantly, because the world over, disposal of solid PFAS contaminated waste is an increasing cost. So I think that's an important consideration. In terms of labour, because we've really focused on an agricultural style of system. As I say, we're not ashamed at how simple our system is. It's a really fundamental principle. It uses pumps, it uses venturis, and it uses valves and pipes. And so all of those readily available, relatively low cost elements that don't require a huge amount of maintenance other than periodic maintenance from time to time. So very low on labour consumption. And then in terms of energy affordability, I noticed a question had come in there before around energy consumption. So we've had the luxury of monitoring the plant up at Okey now for over a year. And while that plant up there has a fair amount of pre-treatment and also has GAC treatment and resin treatment, the SAFF element of it uses about 0.5 kilowatt hour to treat 1,000 litres. So obviously it's depending on what the energy costs are in your particular precinct, but if they're, let's for argument's sake say for industrial energy at 10 cents a kilowatt hour, then you are talking fractions of a cent, tens or hundredths of a cent to treat a single litre of PFAS contaminated water, and that is very low cost compared to some of the other technologies that are out there. So I think that all those points I think are good for a philosophical discussion, and in some ways I think it's embodied in these kind of images that we've got up in the screen, where you look at those kind of systems like the SAFF, very small footprint, relatively low power usage and easy to just drop onto a site. As you move into some of the regen resins and the more complicated systems, obviously a fair bit of engineering goes into that, and so you want to think about, is it a long-term application you've got here? Is it a high concentration long-term application, in which case you might go down that track? Is it high volume, really low concentration? Then you might look at GAC only, for example, but those systems will use a lot of space, a lot of real estate, and create a lot of consumables. So like every decision in life, there's pros and cons with all systems, and we think I think that SAFF has a really important role to play in all of those treatment trains, and we're actually really keen to collaborate with other treatment technology providers, because we think there's somewhere in there's a really elegant mix for every site.
Yeah, absolutely. Thanks for that, Pete. Just again, if you've got questions, we're almost going to go to the Q&A section shortly. So if you've got questions, put them into the chat box. I've got a few coming through here, which we'll come to when we close out the sort of formalised part of the webinar. But before we jump to that Q&A section and close off the webinar, Pete, just there's some stuff that we've been doing in other areas, that downhole foam fractionation, for instance, which is actually where our journey started, and some of the foam fractionation assisted soil treatments. A bit of a taster really for I suspect what will be webinar 4 in this series, but just give us a very brief taste for what we're doing in those spaces.
Oh yeah, man, love to. So I mean, we're looking at all sorts of stuff at the moment. There's heaps of moving parts in the PFAS world, as all of you guys out there are well aware. But I suppose we would like to frame it this way: is that the SAFF plant is like the beating heart of any site's PFAS contaminated water treatment. So at Okey, we've used it in a pump and treat application. So primarily we've taken groundwater extraction wells up there. We happen to have 5 of them, and we're drawing out PFAS contaminated water and we're directing it to the SAFF. But it's certainly that's not the limit to the technology. Like you can use the same system on the same site for surface water treatment. So if you've got water accumulating in culverts, if you've got water accumulating in on-site retention dams, you can of course direct that back to your SAFF plant and treat it. One of the, I think, super exciting areas that we would like to look at is collaborating with RO technologies, because one of the disadvantages of RO is it produces a pretty high level of brine. So 10 to 20% is not uncommon in an RO application. And in drinking water applications, normally the drinking water is harvested out, it's lovely and clean. You've got this 20% brine that then just sort of gets discharged typically further down the stream, and it's not really removing the problem for the environment. But we think by collaborating with SAFF, we can actually separate, concentrate and destroy that PFAS and remove it from the environment as a closed loop application. One of the areas, as you said, mate, where we first started was downhole foam fractionation. So we have worked in the downhole foam fractionation area since 2016, just doing experiments on whether we can effectively use interconnected circulatory wells to create a permeable reactive barrier of air beneath the surface on the downstream gradient of a PFAS contaminated site to progressively harvest that primary fractionate when we're in the ground. So there's a table that sort of shows how that might work in that this is up at one of the defence sites north of Sydney, where we were at a hotspot, and in the groundwater we had about 640 parts per billion. We fractionated an existing well on site there, and we were able to pull out a foam concentrate from the surface that had 130,000 parts per billion concentration in the foamate. The water that was left behind in the well had about 110 parts per billion. So when you run the mass balance on that, you realise that what's actually happening is that well is regenerating itself with more PFAS contaminated water. And so the environment just keeps bringing that in. And so when we combine that with a circulatory well capability, we're getting these interconnected wells that are just drawing in the PFAS contaminated water, and as I say, sort of putting up an air curtain, if you like, beneath the surface that we think is going to work really well. We've actually, we've got some studies going on in collaboration with Uni New South Wales and Macquarie Uni under the Australian Research Council grants that were handed out last year, and those have kicked off now, looking at combining water jets and air bubbles to liquefy the upper layer of the surface where a lot of the PFAS resides, to try and float out that contaminant and then process that through a SAFF as well. And then I guess the last area that we think is important is a lot of these sites we're going to, they have PFAS contaminated soil, sometimes in fairly large volumes. And so how do you deal with that? Well, almost inevitably, no matter who the technology provider is, they wash it. They wash the PFAS contamination from the soil and they try to migrate it into a water body. And so we think that the SAFF system, with a little bit of pre-treatment for sediment removal, is a fantastic capability to treat that processed water and feed it back to the soil washing cycle. So it's a bit of a Swiss Army knife approach, if you like. Like, if you think of it as sort of that sort of central technology that a lot of other contaminated streams can feed into as part of the solution. And then in terms of the output from it, you know, up at Okey, for example, we're using it for irrigation. We're using it, we've got large tanks there where we're using it for our building contractors to come and collect the treated water for dust suppression applications on site. We've got an aquifer re-injection well there where we're able to feed the water back into the aquifer. So, you know, it's sort of you've got to be a bit imaginative, I think, with how you just make the most of these technologies.
Yeah, absolutely. And I think that is a good sort of precursor, without giving too much away, as to where probably the fourth in our webinar series in this PFAS remediation will be coming up. So look out for that. That brings us to the end of the formal sort of webinar, and we're pretty much coming right on time there. Please hang around for the Q&A side of things. We've got plenty of questions that have come through, and we'll answer those. If you've got questions coming out of this webinar that relate to the SAFF, so the separation concentration phases of a successful PFAS remediation project, please send them through to either Peter or Dave on our, I think we're just trying to get the screen there with the email addresses. Just send them through to enviro@opecsystems.com. And if you'd like to get in touch with Dora to look at the AACO system that CDM Smith have been working on, please send your emails through to Dora's email address, CHIANGSTSD, at cdmsmith.com. Again, I just remind those viewers, if you want to take advantage of our predictive modelling and treatability services, again, just send an email through to the enviro@opecsystems.com. Please follow us on LinkedIn and keep an eye out for our next webinar. So thanks for joining us. If you can't hang around for the Q&A, that's great. You will be able to see them on our website when we publish them there. Let's just jump to some of the questions we've got that have come through. So, James, you asked, have you looked at treating AFFF foam and water from hangar tests?
We've done some basic tests. So a lot of the low fluorine and non-fluorine foams are still very amenable to foam fractionation. They foam, so it works pretty well. In fact, the 6.2 FTS heavy ones are amazing. Like, you get this incredible foam coming off the top of that. So the short answer is yes, it works really well for some of the hangar-based firefighting foams that are out there. And we also think there's a whole world you can dive into, James, around re-engineering firefighting training capabilities on sites, so that it's like a bit like a first flash retention system on a service station site. You're capturing all the runoff water, you're putting it through a SAFF style system to remove the contaminant. You can even have water reuse for that fire training application. So yeah, I think we've done a lot of work, and I think there's still a lot of work to do in that space.
Okay. I might just add that where we are presented with hangar deluge foam waste, so it's basically trade waste, and you're trying to remove PFAS from that, we typically just feed that straight through the tertiary fractionation column, because it's going to foam way too much to put it through the primary and probably too much for the secondary. So in that instance, there might be more tertiary fractionators in a 10-foot container or a 20-foot container. But few little tweaks, but we have actually done a fair bit of experimental work with 6.2 FTS foams from a hangar, and it's not a foam that just anyone would want to have a go at, because it's
heavy. It foams.
Yeah. Well, I guess that was why it was introduced for putting.
But we have a methodology now to treat it. It took us a while, but we've got one.
Okay. Rod has asked, with such great results, why hasn't this technology been adopted more commonly in the industry globally?
I don't know, Rod. You tell me. I don't know. I think there's a certain conservatism that permeates our community and our scientific community, and people want tried and tested systems. They want to see it at full scale. They want to see it across a range of sites. So we've been, I think, patient. We've realised that we've got to earn our stripes, and so we've been on our trainer wheels for a year. But with the 1 year anniversary of Okey, and even in the few months preceding that, like I did a sort of global tour in March just before the COVID thing hit. But we think now is the time for us to get that message out there. We've put in a lot of abstracts for presentation at conferences, most of which actually got cancelled. So, in the coming year or two, you can expect to see a lot more of us out there trying to push the message into that global marketplace. And I think once you've seen what it can do and you've got an understanding of just how elegant and simple it is, it's hard to see it as not a part of any treatment process.
And having the physical benchtop labs in both Europe now and the States.
And we've had to invest literally millions into building these systems and getting them up to prove them. So it all takes a bit of time, mate. It's probably the bottom line, but I think the next year or two you'll see some changes.
So it's really up to us to disseminate the information through these webinars and through those research collaborations.
Yeah.
So Mauricio has come back. First of all, he's said that I got his name right, which is fantastic. Thanks for that. He has come back saying mobile, as in you can take them into a site, run it for a couple of months, and then deploy them to another site. Well, that's exactly what SAFF.
Yeah, that's exactly right. So there's a decontaminant. Obviously, when you're starting to deal with concentrates that are 1 million times higher than your groundwater, you want to manage the decontamination and the cleaning of those systems as you move them from site to site, particularly when you're worried about parts per trillion levels. So we have developed a sort of a decon wash process for the SAFF, but it's exactly that, mate. I mean, that's the whole purpose of the design is you plonk it on a site, plug in your power, plug in your dirty water, treat what you've got to treat, and then when you're finished with it, you can take it off site.
So we got David and Mylene have asked a similar question in that what is the power requirements for SAFF 2.0?
Yeah, well, I sort of touched on that, guys, but I'm happy to go there again. It's really, so we've got the data from Okey to guide us so far, and in that instance, we think it's about 0.5 kilowatt hour per 1,000 litres. So, you know, that probably should be translating to between, you know, 1/100th and 2/100ths of a cent per litre to process the water, and we know for a fact that is a very low treatment cost.
Yeah, I guess it's not pushing again, as you said before.
Yeah, there's no resistance.
Membranes,
there's no kind of there's no high levels of
flow.
energy required. It just basically flows from one chamber to the next to allow us to do the treatment.
Really, the only consumable is electricity.
David's also asked, what's the noise level like? Can it operate with the doors shut? How does it handle brackish, high dissolved solid wastewater or solid water?
So, I mean, split that in two questions. So it's not very noisy. I mean, they're standard industrial styles of pumps, and so it's very quiet. You hardly hear it running when the doors are closed. And yes, it's designed to operate completely enclosed. We sort of build it to operate in temperature extremes, from operating out in the desert to operating up in the frozen north. So it's temperature controlled. We've done quite a lot of air quality testing around each of the fractionation stages to see that we're not discharging or volatilising, aerosolising PFAS contamination at any stage. So it can operate in those environments. And in terms of your question effectively around salts, it works better the higher the salt content is. So it's not impacted by brackish or brinish water. It actually improves the performance, is our experience. Would you agree, Dave?
I agree.
Yeah.
Well, actually, Pete, just on that, Doug has asked, which I think you've probably just covered there, but let me just make sure because I'm not the chemist. The air used in the fractionation and the vacuum extraction, the foam extraction, would need to be exhausted. Do you scrub the air used for airborne PFAS?
Yeah, the short answer is yes, Doug, we do. So we've got a commercial activated carbon scrubber unit. It's about 180 litres that's fitted into the container. It discharges to atmosphere. We reckon that system will last for about 30 years before the medium requires replacement. We've done a number of tests to look at aerosolisation of PFAS. It's essentially contained within the system. It's a closed system. It doesn't vent to atmosphere other than via the carbon scrubber. But I should say that the detectable level, that they're non-detectable levels within the plant itself. So you could be standing inside of it and there's no exposure, is our experience.
Okay, thanks. Doug has also asked, do you have a TOPA results for your plant? And what is the reduction of precursor compounds through the SAFF process?
Can you do that one, Dave?
So, Doug, we've previously done lots of sampling and testing for topper analysis in our bench scale. In 2016 and 2018, including the full-scale treatability pilot rig that we had down in our Melbourne lab. But the Okey plant, it hasn't been a requirement for us to do that. Up at Okey, part of our contract with the client is to merely test PFAS for the feed water coming in and the treated water going out. And then OPEC does a lot of internal plant testing for the SAFF plant.
It's worth adding on those tests. We haven't had a single exceedance in 12 months, so the system's worked perfectly.
Okay, so Yu Lang has asked, thanks for a nice presentation, thank you. I appreciate that feedback. And he's wondering what other contaminants beside PFAS compounds could be removed with SAFF?
So anything with a high Henry's constant, we believe would either be foam fractionated up into the foam for vacuum harvesting, or volatilized into an aerosol for removal out of the water column, similar to an air sparge system. We also think it probably also has some ability to remove microplastics, anything that can also be floated or airlifted out of a water column.
Because those polymers have a real appeal, if you like, to an air bubble surface for various reasons. And so in that foam matrix, as it collects, our next kind of phase of works is to look at that microplastics extraction, because in many ways there's a bit of a holy grail there. Like for a water treatment plant, if we're able to remove both the microplastics and the PFAS simultaneously using a foam fractionation process, it's a fantastic outcome.
Yeah. That's one of the things that we've got in mind for Macquarie Uni. One of the researchers there is a bit of an expert in microplastics.
Okay. So I've got a question from Janet. What are the main differences between SAFF and regenerative resin solutions? Sorry, guys, a bit dark on my screen.
No, it's all right. Well, there's a lot of difference. I mean, they're very different fundamental technologies, but there's also some commonalities there. So, I mean, I guess we can explore those. So regenerative resin systems are a system that is able to very effectively remove short and long chain compounds. You get an extension of the life of the resins through the distillation process that sort of reinvigorates the resins for a certain number of cycles. And so I think primarily my understanding of them is in high concentration applications like firefighting training areas or source zones. They have a good application. I think because of some of the complexity around the engineering, they're more expensive to implement. So your payback period typically is longer in that kind of 7 to 10 year window. So they do their job really well. I think where SAFF is similar, I mean, the beauty of SAFF as a technology is that it's concentration agnostic, if you like. It doesn't matter whether you've got 1 or 2 parts per billion or 2,000 parts per billion of background PFAS contamination. Those air bubbles keep rising, that foam keeps forming, you're harvesting it without using any extra input. The disadvantage, I think, of any absorbent media is that it has a certain number of sites available for PFAS collection, and also if you've got cross contaminants in the mix, like that leachate sample from the landfill that we presented earlier, those cross contaminants also take up sites. The beauty of PFAS is it sort of has unlimited sites, if you like the air bubbles just keep coming and that contamination keeps rising. So while I think the main thing to point out is over time, you don't have this escalating OPEX cost with SAFF. You've got a very low and consistent operating cost that really doesn't go up with higher concentrations. And so I can see regenerable resins working in synergy with SAFF, where SAFF is the front end heavy lifter. It takes out what it takes out in that 70 to 90% realm. Of overall bulk detectable PFAS, and then that treated water that still contains a portion of the short change is then directed through a resin plant, be that a non-regen or a regen resin plant. That's a lovely kind of dance between those two technologies that optimizes the life of your absorbent medias and also allows those reduces your costs in the long term.
Hey, this is Dora. If you don't mind, I would like to add.
Yeah, go for it.
All right. So now we're seeing comparing foam fractionation and then regeneration resin is a pre-treatment requirements will be very different. I did not hear you mention that, because for any media you consider there's a potential for fouling, clogging, depending on your water quality. I think for the foam fractionation, you may have a less concern in terms of that.
Yeah, agreed, Dora. Yeah, thanks. It's that is a big benefit, which we probably haven't pushed enough, is that you know that propensity of any media to foul is a limitation of those technologies, and you don't really get that with fractionation because the venturis aren't blocked by cross contaminants. It just keeps chugging away and working. And so, whereas a lot of the work that goes on in water treatment plants is about maintaining and the health and the viability of the resins over time. It's quite a challenge. So yeah, we're lucky not to have to worry about that. So yeah, thanks, Dora.
I've just got a bit of I can't hear Dora, so I'm hearing it through your things. So we've got a question from Kent. Do you have any experience with soil washing for different soil types, and would the soil type impact the application of SAFF?
Yeah, so we've got a limited amount of research, Kent. We've done, as I mentioned earlier, we've got a collaboration with Macquarie and Uni New South Wales, where we're looking at treating the top layer of contaminated sites using a combination of injected water and air. Some of the previous, we're also doing some experiments at our own facility at the moment, just doing a triple wash on various soil samples to see how much is left behind and how effectively we can remove that and treat that with SAFF. In the early days, we did quite a lot of work at the Williamstown site where there was sandy soils. Essentially, the coarser the soil, the more open the mix, the less colloidal content, the more effective the soil washing process works, and also the less residual dissolved solids and suspended solids are carried through for us to have to deal with before putting through the SAFF. So if you're in a really clayey environment, you're going to find more challenges. Doesn't mean it's impossible, it just takes a bit more prepping. If you're in a more sandy environment, you'll find it'll be quite an easy solution to wash that PFAS contaminant out into the water matrix.
We've actually worked up a recipe to wash soil, whether it's sandy soil or more clay alluvial soils, to transfer PFAS from the soil into the wash water, and then do a pre-treatment of the wash water to remove solids, and then treat the clean wash water through the SAFF and recycle that back into the next soil washing process. But I guess we don't want to give too much away until the next webinar.
Well, that's I guess maybe one area we could just touch on is there's amendments available. So you can amend the gas you're using, and you can also amend it using a range of kind of surfactants to enhance the process. And so they're the elements, the variables that we're playing with to try and optimize soil washing, because it's a huge part of the problem that needs to be dealt with.
Yep. I have to say I love a good acronym. So Mary has come through saying, is SAFF the same as DAF?
No, well, DAF.
So what is DAF? Sorry, just excuse my ignorance. But
so dissolved froth flotation is a really old technique of using ultrafine air bubbles in pollution treatment and some mining processes.
Right.
So it does use air bubbles. So in that respect, I guess they're similar. But you might think of DAF as kind of like a really poor cousin to the primary fractionation stage of our process. It'll, in a DAF system, you will see a foam accumulate, but there's no way to harvest it. There's no way to actually take it to that concentration step. So if you look at sparging systems, if you look at DAF systems and various aeration systems in industrial processes, you can generate a foam, and DAF's no different to that. But I think where the art lies with foam fractionation is what you do once you've created the foam.
I think DAF would be a lazy foam fractionation column, in that it's a shallow bath. The foam's allowed to sit on the meniscus for a long time and it redissolves in the water. It's not removed instantly, whereas foam fractionation or SAFF, we are absolutely optimizing it to remove all the PFAS that we can target out of that water column as fast as we can, and as soon as it hits the meniscus, we're getting it ripped off instantly.
Yeah. Okay.
And creating really dry, crisp, super small volumes of concentrate. So it's the opposite of being lazy.
Okay. That pretty neatly brings us to the end of the Q&A. I don't have any more coming through. Look, I appreciate Dora just for hanging around for the Q&A side of things. I
Thanks,
appreciate
Dora.
it's the middle of the night for you, and then you're joining us for the other 2 webinars we're running. Thank you once again for joining us. One of these 3rd webinars will be published on our website, and we'll send you details of that. Feel free to share it amongst your colleagues. Thank you to my colleagues on the sofa. We would normally do a handshake at this stage, but we won't now. So thanks, Pete. Thanks, Dave.
Thanks,
and Dora, thank you so much for joining us in this webinar.
Thanks, everyone. Stay safe out there. We'll see you soon.